In a reservoir, we might find oil, water, or gas. Let's talk about reservoir water. Many oil reservoirs are composed of sediments that were deposited on the ocean floor. These sedimentary beds were originally saturated with salt water. In the process of oil accumulation in the reservoir, part of the water was displaced. The water that remained in the formation was given the name connate interstitial water. Connate from the Latin meaning born with, and interstitial because the water is found in the interstices or pores of the formation. By common usage, the term connate interstitial water is now referred to as connate water. In the petroleum industry, we refer to the percent of total water saturation in equations as S sub W. We refer to the percent of irreducible connate water saturation as S sub Wi, and we call it wetting water. Wetting water will not flow, and it will remain in the reservoir rock even when oil and gas might be flowing in the same pore spaces under the influences of relatively large pressure gradients. So wetting water, let's look at it. Oil, which is lighter and does not mix with water, makes room for itself in the pores of reservoir rock by pushing the water downward. Nevertheless, oil will not displace all of the water. A film of water that sticks to or adsorbs by the solid rock material, sand grains, surround the pore spaces is called wetting water. Wetting water usually coats the sand grains of reservoir rock. And the reason for that is that most reservoir rock was marine wet first. Why are we concerned with wetting water? Well, let's look at it. Number one, it can reduce permeability. So with a reduction in permeability, our oil doesn't flow as well. Wetting water also takes up space. There's only so much pore space, a percent of the total volume of the rock. Therefore, if some of that pore space is taken up by wetting water, and wetting water could be higher than 10%, there is less space to hold oil. So if an engineer did not account for wetting water, he or she could overestimate the amount of original oil in place in the reservoir. And that could be a very costly mistake. Let's look at a problem, something like you might find on an exam. If you drill 2 wells in a sandstorm formation, which formation would you expect a larger amount of wetting water to be? Why? Well, let's look at the 2 formations. We have well A and well B. Well A drilled into a formation with relatively small sand grains when compared to the formation that well B drilled into. Well B drilled into a formation with relatively large sand grains when compared to the formation that well A drilled into. Think about it for a second. Let's look at the answer. Well, here's the answer to the problem. The answer is well A would have more wetting water. Why? Because it is drilled into a formation that has smaller sand grain size than the reservoir that well B drilled into. If 2 reservoirs of equal size, the one composed of smaller grains of sand will have larger amounts of wetting water because there is more surface area to adsorb the water than the surface area found in a reservoir with larger sand grains. Let's go away from the reservoir for a second and kind of understand this concept of more surface area. Under food for thought, suppose you had a glass of water on a hot summer day and you were given 3 cubes of ice to cool your water so you can enjoy a nice cool glass of water. The 3 cubes of ice would cool your water. However, if you were to break the cubes of ice into 2 smaller cubes of ice, and put the 6 pieces of ice in your glass, you would be able to cool your water in your glass more quickly because there would be more total surface area making contact with the water. Likewise, in a cubic foot of reservoir, if the sand grains are smaller, there will be more sand grains and more surface area to retain wetting water.